Okay, so good morning, everyone. So welcome to the MoCaO Lectures for 2024. So today, Vera will give a second lectures on conic programming and duality and constructing convex sets. So Vera is an associate professor at School of Mathematics and Statistics from UNSW Sydney, and so she will give a second lectures today. Okay, over to you, Vera.
Thank you very much, Tom. So I'm going to continue today. And yesterday, I would say that I planned a bit too much. So I couldn't finish everything I wanted to talk about yesterday. So I will continue on that stuff today. I will talk about conic programming and duality. And of course, it's quite light, right? So I'm just going to show you some things that are fairly basic about conic programming to more motivate maybe the studies of convex sets and convex cones. And I have selected a couple of beautiful but very well-known things. So for those of you who know them, will be very familiar. For those of you for whom it's not something that you would do, I hope that it will be fun and interesting. And then I will talk about constructing convex sets. And so the stuff that I was talking about before now, and the stuff that I'm going to talk about for about half of this lecture today, it's very well known and it's just basic things, right, in the field. And then when I talk about constructing convex sets, I will go over basic ideas about how to construct convex sets using Simon-Minkowski addition or intersections or slices, right? And I will use examples that come from my own research because, well, I know that is another thing, and also I think it will motivate things well. So, okay, let's continue. And please use the chat if you have any questions or comments. Please use the chat to comment on whatever I'm talking about. So I have chat right next to my slides, and I should be able to see what you're saying right immediately. All right, so remember last time we were talking about the semi-definite programming. We started with linear programming. And of course, we can look at general conic programming. And so the thing is, you can formulate some problems as some kinds of conic programming problems. There's all sorts of different cones that are useful for formulating real-world problems or problems that come from pure mathematical challenges and so on. And for some particular cones, we actually have very good software to solve those problems. We have excellent software for linear programming, semi-definite programming. There are some methods for hyperbolic programming and so on, right? So let me just go through this basic model. Yeah, then I will talk about more things. So we would usually maximize and minimize the linear objective function. We'll have a linear constraint and a conic constraint. So previously, the conic constraint would be linear programming, something like x greater or equal to 0 as in a vector, right? Or which is the same thing, x will be in the non-negative orthant. In some other cases, it was the cone of positive semi-definite matrices. So say x here was a matrix variable. But in general, we can set up a conic programming model and look at just the model itself. And I just want to motivate a couple of things. So I want to show where conic duality comes from. And that will also demonstrate why we have dual cones and where dual cones and dual objects come from in the context of conic programming. So you can look at it from different perspectives. You can think about normal cones, just define polars and normals to polars of convex sets, normals to convex sets and convex cones. But I want to also motivate things from the very basic, very classical duality. But first, also, let's go over the question why cones are so popular. So as I said, some problems are typically formulated through conic programming, right? So why do we want to formulate a problem using a cone and not just general convex set? Well, for one, is closed convex cones are essentially compact objects, right? So if I take a closed convex cone, I can talk about all sorts of convergence and I can use compactness because I I can look at all those rays in the cone as some equivalence classes, right? And because things are closed, or I can think about slicing the cone, right? So if I have a pointed cone, a cone that has 0 as a face, I can slice that cone and obtain a compact convex set that will tell me everything about this cone, right? So cones are essentially compact, and I can formulate, on the other hand, a conic programming problem that has an unbounded convex feasible region through those kind of compact objects, right? So it's a very basic example, right, of a conic section. So I have a second order cone or circular cone, and I slice it with a linear subspace or an affine subspace, and then I obtain a convex region that is closed and bounded and can have complicated, right, geometry. But I can study it through convex cone. So I will talk about duality in a moment. Splitting constraints into conic and linear is very convenient for duality. And yes, and I guess, yes, so also, as I said before, that conic models allow to deal with problems which cannot be represented in maybe a more classical way when you take when you can represent constraints through some convex inequalities, for example. All right, so let's look at duality. And again, this is just a very classic trick and the motivation. I'm not going to go in depth through this. So pick some form of a conic problem. So for example, something like this, right? Minimize linear function, C transpose X, subject to linear constraints, so just a linear system, and conic constraints. So I have my variable in subclosed convex cone K. And let's write a dual problem, but only coming from the most basic version of duality. So there is, in my opinion, a fascinating fact, right? That if you take any two sets, any sets, you don't need to worry about the space those sets are coming from, any two sets. And you take any function that maps the product of those two sets to the real values, right, to the real line, then we always have this weak duality, right? So you don't need anything for this weak duality. You don't need continuity of this function. You don't need any properties. This stuff always works, right? So the infimum over the first set, the first variable, and it takes a primum of, so it takes a primum over the second variable, right, of this arbitrary function is always greater or equal to the other way around, right? Supremum of infimum. So it's also very easy to prove, right? So there's no magic here. So the duality in conic programming, Lagrangian duality and all those things, they come from this relation. It's just that the struggle is to obtain the opposite inequality, right? So the struggle is to actually make sure that instead of an inequality, we have equality here. So when we have one problem that is a primal problem and another problem in which we just swap supremum and infimum, how to make sure that the values coincide, because then we can solve, right, the dual problem, obtain a bound from the primal problem, and we know the duality gap, right? So we know how close we are to the solution if we can actually ensure that for a class of problems or for some particular problem, these two things coincide. So there's all sorts of things like minimax theorems and various developments, right, to get the equality in this duality relation. So, but let's get the dual conic problem just from this very basic thing, right, that doesn't assume anything, doesn't require anything. So how do we, and you can obtain duality for pretty much anything, right, for using this trick. So first of all, I look at my problem and I'm going to rewrite it as an infimum and supremum here. So first I'm going to say, well, minimum, infimum, let's replace minimum with infimum, which if the infimum, yeah, so if the minimum is attained, right, it doesn't matter, but sometimes it's not. And I'm going to talk about this soon. Okay, so let's write it like this, infimum of this linear function. And then we'll write a constraint such that ax equals b and x is in k. Okay, so the first thing I'm going to do is I'm going to tuck this thing inside here somehow. So I'm going to remove the constraints from the infimum and put them elsewhere. So the first trick is very simple. I'm going to put a supremum here. Right, C transpose X, keep this thing. And then to incorporate this linear constraint into somehow this function, I'm going to add some parameter, say lambda, and write ax minus b here. So if b was in Rm, then lambda here will also be in Rm. So, and yeah, so we keep x in k. So what happens here? So if I look at why the values of these things coincide, right? So when I look at this supremum, if ax equals b, if this is 0, then the value of this is exactly C transpose X, right? If ax minus b is not 0, then because I'm taking the supremum over something here, this guy will be plus infinity, right? So this expression will be plus infinity. So somehow by writing things like this, I make all points that do not satisfy this equality irrelevant, right? Now, the next step is something that I really wanted to do because it's a very clear way to see the motivation for defining dual cones, right? So now I want to take this and also move it there by using an appropriate object, right? So I cannot use a linear thing like this. So I want some object such that if I take a supremum over something, right, using that object, if x is in k, I will get 0, right? So it doesn't kind of affect the value of the objective. But if x is not in k, then I will get plus infinity. So again, I remove those values, right? So this is how, in terms of conic optimization, how the dual cone emerges, right? So I'm going to continue writing it like this. C transpose X plus lambda transpose ax minus b. And then I need something else that will do the same thing with this conic constraint. And so the dual cone, we can define it like this. So the dual cone to k is all points y such that I'm using this transpose thing. So x transpose y, or the inner product between x and y, is greater or equal to 0 for all x in k. Right, so if I have my cone k that looks like this, then the dual cone will maybe look like this. So right angles here. So this guy will be the dual cone. And a really cool thing is that also, if my cone is closed, if my cone k is closed, then when I take the double dual of a cone, I will get exactly the same cone, right? So the double dual will be the closure of k, but if k is closed, then it will be just k. K is closed. So now we can put it in here, right? So how we're going to do it? Well, we're going to observe that now the supremum over somebody in the dual cone and then here we're going to put x transpose y. Right? So because of this bipolar theorem or biduality of convex cones, so what we're going to have is if x is in the original cone, let's put minus here. So if x is in the original cone, then, well, I have this inequality, right? X transpose y is always greater or equal to 0. So I will have the same for my bidual cone. So what will happen is that I will have 0 if x is in k. And if x is not in k, then I will find some point here such that this inequality will be negative, right? And then because we're dealing with cones, I will have plus infinity here. Okay, so now I can simply plug in this dual cone into the supremum here. So I can say I have some mu in K star such that here I will put minus K star here. So here we'll have mu transposed X. So I have completely moved all constraints under the supremum. And now I can swap supremum and infimum and obtain the dual conic programming problem. So hopefully I didn't make any mistakes. Right, so so we have, now I'm going to use the weak duality, right? So the same, so now I'm going to say that this is greater or equal to the supremum. And here I'm going to put the same things. So lambda in Rm, mu in minus K star. And then I swap infimum and supremum, and I put infimum over X here. So this was just X. And I can group things and use the same trick, right? So now I'm going to say, okay, I put C transposed plus lambda transposed A plus mu transposed X here. And because X is unbounded, so X is just from the real space, from Rn. This guy will be minus infinity whenever the thing in the brackets is non-zero, and it will be equal to, oh, sorry, and I also have to have the remaining term, minus lambda transpose B, right? So this guy will, when this guy is zero, the infimum will be minus infinity. When this guy is non-zero, when this guy is zero, it will be zero, right? And when it's not zero, then it will be minus infinity. So then I simply have the supremum over lambda in Rm, mu in minus K star. And then this expression should be zero. C transposed as lambda transpose A plus mu transposed, or without even transposed, I can write it more directly. C plus A transpose lambda plus mu. This should be equal to zero. And so this term disappears, right? So I'm going the other way around, and I have minus lambda transpose B, the supremum of this function over these constraints. So that gives me a standard dual conic programming problem. I can write it as y transpose B, let y equal minus lambda. Y is in Rm. And then here I can simplify this whole thing by saying that C minus A transpose Y is in K star. Right, so I got a dual conic programming problem. So dual cones appear very naturally when we try to obtain the dual, when we try to use this weak Lagrangian duality or weak duality theorem on our conic programming problem. Right, and this is the way to obtain duality for all kinds of formulations, not necessarily conic programming, but all sorts of convex programming problems. Okay, so now one thing that I mentioned is that I'm not going to talk about it a lot, is that you need some extra conditions, right, to ensure that this is actually equality and not one-sided inequality. And we know that this latest condition holds, that is if there exists a point in the interior of the cone or in the relative interior of the cone, such that for this point, the linear equality is also true, then strong duality holds. So we always have equality in those two parts. However, what can happen is even when the strong duality holds, so we have the value of primal and dual problems coincide, we actually may have the case in which the value the optimal value is not attained at any point. And there's a very simple idea how to see that whenever the conic programming problem is over a cone that is not polyhedral, we can always find some conic programming problem over that non-polyhedral cone, that specific cone, for which we cannot obtain the optimal value of the objective function. And for strong duality and for this constraint, Slater's condition, I believe that Bruno is going to tell you more about how to impose that condition on the problem. And I think also Isabel will talk more about the duality and about the dual cones and also polars of convex sets that correspond to kind of the compact idea that is equivalent to the idea of dual cones. Okay, so there is a very nice statement that is not all that well known, that if we have a closed convex cone in a finite dimensional space, then it is polyhedral if and only if all of its two-dimensional projections are closed. So if I have closed convex cone that is not polyhedral, so if I'm thinking about a conic programming problem, then it's not a linear programming, right? Some other conic programming problem. Then I can always find some two-dimensional subspace on which, if I project that cone, the projection is not going to be closed. So, and that problem with non-closed projections, it generates most issues with convex geometry. So when we look at all sorts of properties that tell us, okay, this convex set or this convex cone is not good because some condition is not satisfied, in a lot of cases, it's because if you take a closed convex cone and you think about projecting that closed convex cone in different linear subspaces, you can always find some linear subspace, and in particular, you can always find a two-dimensional subspace on which the projection of that closed convex cone is not closed, right? So let's write a conic optimization problem for an arbitrary cone for which there is no optimal solution. So the Slater condition is satisfied, but there is no optimal solution, right? So I will have, yeah, so let's do it. So take any cone, take any closed convex cone. So then by the theorem, right, it's not polyhedral. And this stuff is very old. The theorem is from 1950s. So this is a closed convex cone, it's not polyhedral. So there is some projection on this convex cone onto a two-dimensional subspace L that is not closed, right? So there is some two-dimensional subspace L such that, so let's see, C is the projection of K onto L is not closed. Okay, so you see the picture here, right? So actually, it's a very basic example. So I have like a second on a cone or a circular cone, right? I'm projecting it onto this two-dimensional subspace that is touching its boundary somehow, right? And if my cone is such that, let's say, this ray, right, is orthogonal to this supporting plane to this cone, then if I project it along this direction, right, I project it orthogonally onto the subspace, then the projection will actually be the set, right? So it will be like a half space with the 0 included, but the boundary of the rest of the boundary of this half space will not be in the projection. So now what I can do, so I'm going to pick a point that is this bad point. So there will be some point X and the closure of C, but not in C. And also there will be some point Y. That will be in the relative interior of C. And now Oh, I was using a different notation for relative interior. So now, if I have something in the relative interior and something on the boundary of my set, then what will happen? So I have my set C. Oh, I have my boundary, right? So I pick a point here that is on the boundary. I pick another point that is in the relative interior of C. Then actually all points between Y and X, they're going to be in the set C. They will actually be in the relative interior of the set C. So if I write something like this, X plus T, Y minus X, that point will be in C. All T from 0 to 1. But beyond X, this is not going to happen. So for T less than 0, this is not going to be true, right? Less or equal to 0, because the set is convex, so the projection of the set is convex, and so on. And so I can write down an optimization problem in which I will use the fact, right, that I can't, that this point is on the boundary of my projection, but not in the set. So if I say I want to maximize, say, X minus Y transpose some vector U, right? So I want to choose my objective function that is pointing in this direction, and I want to find the maximum. And then I will have a linear constraint that I can write like this, X plus, so I will cut it with a linear subspace that goes through this point Y. So I will say X plus span Y minus X. And then I'll take the orthogonal complement of L. Then, and U and K, then this optimization problem is not going to have an optimal value, right? So because when I try to find the maximum here, and I substitute my U in this formulation, then what I'm going to have, right? So if U is in here, U is in K, and U is in the set. Then when I look at the objective function, X minus Y transposed, I will substitute X plus T, Y minus X. So this part will disappear because X minus Y is in L, and it's orthogonal to this orthogonal complement. Right? So we'll have something like this. And then I will have X transposed, X minus Y minus T, X minus Y norm squared, right? So because of this condition here, right, I'm going to have maximum of this not attained, right? Because the supremum of this is going to be 0, but it's not going to be attained at no point, right? Not attained. So there's always this problem with no matter what conic programming problem you take, there's always a potential problem with not attaining the optimal value. So it's impossible to find some kind of a generalization of polyhedral cones that will be non-polyhedral, and so that any problem over the set will attain maximum or minimum, right? Any conic programming problem. All right. So, but this really is the main issue with a lot of conic problems and a lot of general convex problems as well. Okay, anybody have any questions or any comments or corrections? All right, so then I will continue with constructing convex sets. So now, as I mentioned before, there are famous problems, right? So there are problems in representation. For instance, if we have if we're given some kind of a problem that looks like a conic optimization problem, we don't always know how to formulate that problem as semi-definite programming or some other easier problem that we can solve. And one of the very famous problems of that kind is generalized Lax conjecture. You take hyperbolicity cones and problems over hyperbolicity cones, and we actually don't know if it's possible to formulate those problems as semi-definite programming problems. Right? So it's important more for theoretical study, for trying to see where can we push things and where things are not equivalent, to be able to construct examples that demonstrate somehow where things can go wrong. So this constructive approach to convex set, right, can help, for example, with building worst case examples to prove complexity bounds. And you can think about some very basic examples, not basic examples, but very well-known examples like the clean inter cube for linear programming. It's a whole set of examples that shows that no matter what version of simplex method for linear programming we take, right, we can produce a polyhedral set for which simplex method will perform badly. A similar thing is to clarify how geometry affects the performance of numerical methods. So sometimes we have a numerical method and we can't prove convergence, or we struggle with seeing why it doesn't work. And in many cases, when we deal with convex problems, the issue is that we can't think of an example on which the method fails. So we cannot actually identify the properties that affect that poor performance. And also, as I mentioned, it's important in obtaining negative results in problems related to representations. So if I have a class of problems and I want to represent them, say, as semi-definite programming, then if I prove that there is an example in those problems that doesn't satisfy some property that all semi-definite programming problems satisfy, that means that, well, the problem is hopeless, right? So negative results are important, and knowing how to construct convex sets is useful for at least that kind of research. And then it's also interesting to see how much we can learn about the spaces themselves and how much we can understand about the convex sets themselves, right? What can we get generally for convex sets? All right, so I'm going to...
Vera, may I ask a question?
Yeah.
Am I correct in understanding that the reason that representation is so important is because, for example, I might have a problem that's representable in terms of hyperbolicity cones, but if I could represent it in terms of positive semi-definite cones, then I might be able to use a faster technique or better methods? Is that a correct understanding?
Yes, and in particular, for example, for that specific problem, hyperbolicity cones, the duals of hyperbolicity cones are not hyperbolicity cones. So actually, duality is a lot easier for semi-definite programming problems, right? Because the primal and dual problems are the same kind of problem, but it's not true for hyperbolic programming. But also, if you think about it so that it's a practical implication of that. But if you think about that in generality, not in generality, but maybe in more theoretical kind of context, it's just an example of a problem. So if we don't know the answer to the generalized Lax conjecture, it means that we don't understand semi-definite representations. So if we solve the Lax conjecture, like we produce a counterexample, or we find a way to represent hyperbolicity cone as a spectrohedral object, then we will learn a lot about spectrohedral representations, right? We will maybe know how to represent other objects as spectrohedra and so on. So yes, that kind of thing. And I think I have
That makes sense. Thanks.
Yeah. I think I have used an old version of my slides that has some repetitions. So I hope that this still has some corrections. I think I opened them before and didn't change. Anyway, so let's look at some particular things. And again, so this comes from some things that I worked on with my collaborators, but it demonstrates different ways in which convex sets can be constructed, right? So we're going to look at compact convex sets and their faces. And we will look at something that we now call facial dimension signature of convex sets. So every convex set has a dimension associated with it. That dimension is an integer. If the convex set is non-empty, it's just a non-negative integer that tells me what is the dimension of the affine hull of the set, or the smallest affine subspace that contains the set. It could be a line, a hyperplane, whatnot, right? So faces of convex sets are also convex sets, so every face has a dimension. And then I can look at my convex set and count dimensions, or write down all possible dimensions of all faces of this convex set. So if I take the Euclidean ball, for example, then I have the ball itself. The dimension of that ball is the dimension of the space. So here I have a ball in 3 dimensions, so the dimension is 3, right? I look at all other faces. They are just the points on the boundary. The dimension of those points is 0. If I look at polytops or polyhedral sets, then I have all possible dimensions, right? So if I have a polytop, then the dimensions of faces will go from 0 to the dimension of this polytop. So I have vertices, edges, and so on. Then the last 2 objects in these pictures, they're just examples that show all remaining possibilities for 3-dimensional space. So we have, for example, if I cut the Euclidean ball in half, then I'll generate a 2-dimensional face. So the faces will have dimensions 0 to 3. I have another object that like 2 cones put together. That object will have dimensions 0, 1, 3. So I call those dimensions spatial dimension signature. Now, the question that will demonstrate how to use Minkowski sums for construct convex sets is given some finite subset of non-negative integers. And for simplicity for this lecture, I'm going to assume that that set contains 0, because then I can deal with compact convex sets alone. Can I construct a compact convex set always that this finite subset is a facial dimension signature of that compact convex set? Right? So if I write anything, 0, 3, 7, 25, can I then produce a convex set, compact convex set, for which faces will have these exact dimensions? And so this question can be solved with Minkowski addition. Minkowski addition is very close to taking convex hulls, but it's a slightly different thing, and it can be very useful, and it can also come up in applications, right? You may actually end up formulating a problem in which the constraints are Minkowski addition of some convex set. So Minkowski addition of 2 sets, not necessarily convex, is just the sum of all points from one set and the other set, right? So I take the first point from the first set, second point from the second set, and take all possible sums, right? So here on this picture, I take a line segment, and I add the disk to this line segment, and then the set that I obtain as the Minkowski sum will look like this. So of course, I would have 0 somewhere. It's a set in 2-dimensional space. Maybe I'll put 0 here, but the shape will be the same, right? So effectively, I take all points from one of the sets and I add them to all points in the other set. Right? So something like this, I will obtain a set like this. And what I can say about Minkowski sum is that every face of the sum can be represented as the sum of some faces of the 2 original sets. So based on this construction, I can actually build any facial dimension signature I want by adding Euclidean balls to each other. So for instance, I want to get 0 to 3, then I will take the disk, right? Put it in the 3-dimensional space. It has dimensions 0 and 2. I will add the Euclidean ball to this disk, and the set that I obtain will have a facial dimension signature 0 to 3. This will happen because the only faces I can obtain in this sum come from sums of faces of those 2 original objects. And for the Euclidean ball, when I can add so I can only obtain faces of dimension 3 and faces of dimension of the faces of the object that I'm adding, right? So here I get faces of dimension 0, 2, and 3 because of how Minkowski addition works. If I want to get that faces of dimension 0, 1, and 3, I will start from 0 and 1, take, say, the line segment, right? So it has faces of dimension 1 and 0, and add the Euclidean ball to obtain 3 here, right? So I will be getting faces of dimension 3 and all the original dimensions of the first object, because I will be adding them to just single points on the boundary of that object, and so on. So I can obtain an object with this facial dimension signature, even though it can be obtained from a polytope. This construction allows me to get any kind of sequence. So that is a way to use Minkowski addition to solve a kind of a more like a theoretical question. Now, the problem with Minkowski addition is that the sets that I obtain are not facially exposed. So I can't generically, right, when I add a Euclidean ball to something like this, I can't actually, for some of these faces, I can't slice them off with a hyperplane, right? So they're not exposed. So a face here, for example, a zero-dimensional face, cannot be cut off by a plane from the set, by a supporting plane, because I will have to include part of the boundary here, right, in this hyperplane. This one is actually an example from Rockefeller's book, but there's no pictures in Rockefeller's book on convex analysis, right? So it's that this example is given there as the convex hull of a torus, and also here I have unexposed points, right? So it's almost like a generic thing from the Minkowski addition, especially addition with Euclidean balls, that I get an exposed set. So the next question is, how can I obtain sets that have a given dimension signature, facially exposed, or are, say, spectrohedral? And I can do something simpler, and I can use intersections of convex sets. Right? So I was talking about this in the beginning, that to construct convex sets, so to obtain convex sets, or where convex sets usually come from, is convex hulls, intersections, and I said something else, and algebraically defined sets, right? So Minkowski sums are like convex hulls. So you see that there's some problems, but yeah, you can resolve some questions with that. Intersections in this context work a lot better. So now I'm going to answer the same question using intersections of convex sets. So suppose I want to build a set that has the dimension signature 0, 2, 3. So I will start with the Euclidean ball that has signature 0, 3. Right? So that's the dimensions of its faces. And then I'm going to attach or graft a face of dimension 2 to this Euclidean ball. So what I can do is intersect it with a half space. So I'll take some plane, right, cut off the top of the set. And that will generate a face of dimension 2. I can do it with anything else. So I look at my dimension sequence. I take 0 and 3, for example, for this one, right? And then instead of cutting off a plane, I will use a cylinder and intersect my Euclidean ball with some cylinder. Right? So I'm intersecting with another convex set that is kind of something cylindrical like this, and that will slice off a bit of this Euclidean ball and generate one-dimensional faces. And I can do both on different sides of this set, right? And there's a lot of sides of the set, so I have a lot of surface to work with. So now any sequence I write, this works exactly the same in space of any dimension. I will look at the largest number. I will get the Euclidean ball that corresponds to this number. And then for everything else in between, I will just construct convex sets that are something in between cylinders and balls and planes, right? Just a generalized kind of cylindrical surfaces, and slice off different bits of these sets. So the problem can be resolved by something like this. And in fact, In this case, those sets will also be spectrohedral, just because they can be defined by convex quadratic inequalities. So here you see it's something like this, some kind of a cylindrical set. It's always possible to find C and R in such a way, like the center of the cylindrical set and the radius in such a way that they wouldn't intersect with each other. So they will very neatly slice off faces of different dimensions. And then I slice off, and then I construct a convex set with a given facial dimension signature. So why is this even important? Because it has a direct impact on representation problems. So I don't actually know what is the most efficient spectrohedral representation for something like this. But if in some sense, I have a facial dimension signature, and I say, okay, if I'm representing this facial dimension signature with convex sets from this particular class, then I can't do better than that many. I can't do better than that many inequalities, or I can't do better than a spectrohedron that is defined by matrices of such and such size. That gives me a complexity bound, because then I can look at some problem, count the dimensions, and say that, well, I can't represent this with a very small spectrohedron because of this result, right? I don't have this result, but that's the idea. So now any dimension signature can be represented as a convex set that is the intersection of the number of dimensions minus 1 convex quadratic inequalities. In some cases, we can actually do better. So for instance, I can look at a set defined by, let's say, for this example, a 7-dimensional set defined by 3 inequalities. So the first one is on the first coordinate, x1 squared less or equal to 1. I actually get a line segment, but only in that space, 1-dimensional space. The second one will be a disk, but it will be living in its own 2-dimensional space, right? Not embedded in 7-dimensional space. And the last one will be a 4-dimensional ball. So now I'm going to construct a convex set by taking the direct sum of these sets, right? So a very basic idea of a direct sum is if I want to generate something like a cylinder, for instance, right? This finite or a finite compact cylinder, then I can get it by taking a line segment in 1 dimension, right? And then adding a disk in a 2-dimensional space, right? So I'll get 3-dimensional set that looks like this. Okay, so now when I construct the direct sum, what happens is the faces of the set that I obtain as a direct sum, they are direct sums of faces of the original sets, but also it works the other way around. So every pair of faces, or in this case, we have 3 objects, right? Every face I pick in the first set and the second set and the third set, they will generate a face of a direct sum, simply because those objects live in different spaces and we kind of cover anything with this. So when we do this, then the dimensions of the faces of what I get in the direct sum are the Minkowski sum of the dimension signatures. So if my sets have certain dimension signatures, in this case, the line segment has dimension signature 0, 1, the disk has dimension signature 0, 2, and the Euclidean ball, a 4-dimensional Euclidean ball, has dimension signature 0, 4, then I will obtain the signature that goes from 0 to 7 and covers all numbers. So in this case, I can represent actually any dimension signature that is complete and goes from 0 to 2 to the power k minus 1. Okay, some, let's say, positive integer, through only k quadratic inequalities, convex quadratic inequalities, and that's log 2 of the cardinality of the set compared to cardinality of the set minus 1. And so I actually arrived at an open problem. And an open problem is to find the the smallest number of convex quadratic inequalities that can represent a convex set with a given dimension signature. So we know something. For instance, if just that integer set can be, if it can be represented as the Minkowski sum of some other integers, then we know that we can realize this signature as the solution of that many convex quadratic inequalities. So it's like an upper bound, right? So we don't know if we can do better. And also we have a lower bound, and the lower bound is that we can't do better than some kind of a combinatorial estimate. So the minimum number of integers such that our dimension signature is a subset of something like this. So it's just this bound also shows that that construction for 2 to the power k minus 1 is optimal, right? So we actually don't know the answer to the general question, but I think this shows already several very simple ways for constructing convex sets with the desired properties, right? So we can use Minkowski addition, we can use intersections, and we can use direct sums of convex sets to obtain something interesting, to obtain some interesting convex set. So there's some open questions that I really like. So the first question is that we don't know if we're given a set of non-negative integers, what is the smallest number of convex quadratic inequalities that define a convex set with the signature? Now, if I want to represent this as a spectrohedron, I can't obtain a spectrohedron representation from convex quadratic inequalities, but I don't know how to obtain an optimal one. What is the smallest cone of positive semi-definite matrices such that I can obtain a spectrohedron from this cone that has the spatial dimension signature? I don't know what is the smallest spectrohedron such that I can obtain this dimension signature as a projection of that spectrohedron onto some linear space. This is a really cool question. I don't know if it's possible to construct compact convex sets with desired signatures such that both those sets and their polars are facially exposed. And polars, I think, will be mentioned in subsequent lectures, not by me. And a polar is something that corresponds to the dual cone for convex cones, right? So if I have convex cone K, and I look at the negative dual of this convex cone K, then I can think about polar sets as intersections. So something like this will be a primal set, I see. And if I intersect, if I'm in a standard setting, I will have to intersect my cone with something at distance 1 from 0. Right, and with a parallel subspace, that will be a polar of the convex set, right? So I'm looking for primal and dual objects being both facially exposed. And also, we don't know how to even formulate and solve this problem for an infinite dimensional convex set. So I don't have a formulation for this. Okay, so I wanted to show you something else. I hope I still have a few minutes. And that is a little bit, that also demonstrates some techniques for constructing convex sets, but maybe a little bit more involved and less, let's say, less traditional. So it's not yet published. It's related to my research with Bruno Lorenzo and James Saunderson. So in this case, I want to construct a counterexample to a conjecture. So, and again, this is all about representations. So there is a particular property of convex cones called projectional exposure, and it's formulated in a very simple way. So if I can take my closed convex cone and project it onto one of its faces, onto each one of its faces, right? So for every face, I can construct projection mapping, not necessarily orthogonal projections, but the linear mapping that maps the cone to the linear span of the face, and fixes all points of the face. And then I call this cone projectionally exposed. And we had a conjecture that the intersections of projectionally exposed cones are projectionally exposed. And that's actually related to representation problems, because still until now, we don't know if spectrohedra are projectionally exposed. So we know that the cone of positive semi-definite matrices itself is projectionally exposed, but we don't know if we intersect the cone with a linear subspace, whether that thing is projectionally exposed, right? And that, of course, is important for understanding what can be represented through what kind of objects. So a complication with resolving this conjecture in positive or negative is that we knew that it's true for n less or equal to 4. So in 4-dimensional spaces, the intersection of two projection exposed cones is projection exposed. So we wanted to construct a counterexample in dimension 5. So how can we do this? So the first thing that we can do when we work with cones is to take slices. So if I'm careful with how I take a slice, then I can, the facial structure of my cone will correspond exactly to the facial structure of the slice. Right. So if I have a pointed cone, pointed convex cone that has 0 as its face, then I can always slice this cone with linear space of dimension n-1 if the cone is n-dimensional, and obtain compact convex set that has faces matching pretty much exactly the facial structure of the cone. So one thing that we can do when we try to construct cones in high dimensions is we can take a slice and we try to construct a compact convex set that has desired facial structure. And then it's an opportunity to state the Minkowski theorem that in finite dimensions has a very simple form. If I have a compact convex set in any finite dimensional space, then this compact convex set is the convex file of its extreme point, right? So extreme points are faces of this convex set that have 0 dimension, right? So, right, if I take a tetrahedron or polyhedral set, then the vertices will be the extreme points, right? So they are faces of dimension 0. And this is a very nice example. I don't know what reference this comes from, but kind of everybody who works with these kinds of things, with convex geometry, knows this example. It's a very nice example because it shows that a compact convex set, it's a convex file of its extreme points, but the set of extreme points itself is not compact, right? So this theorem works even when something goes, well, a little bit funny with the set of extreme points itself. So here I have a circle and an orthogonal line segment. I take the convex hull. So I have like two convex cones connecting with each other, somehow generating one very long face and other faces, very long one-dimensional face and other one-dimensional faces that look like this. Right, so in this case, these tips are extreme points. Everything here is an extreme point, but this guy is not. Right? So the theorem works for anything, even something like this. Okay, so if I construct compact convex set, maybe I will have a bunch of curves or something like this, and take the convex hull, and that will be my compact convex set that resolves whatever question I have. Now, another thing that we did, I think I'm running out of time, is designing faces using three-dimensional surfaces. So what I can do here, so remember the question was to design something that a cone that cannot be projected, to design two cones. Each of them can be projected onto some kind of faces, right? All faces of those cones. But if I take the intersection of those cones, then the property disappears. So one trick that we used is three-dimensional design. So we can see things in 3 dimensions. We can use three-dimensional geometry. beyond that, things get complicated. So I take a 5-dimensional cone and I slice it with a 4-dimensional space. So now I'm designing faces of a 4-dimensional set. And I can think about this as, by analogy, with designing faces of 3-dimensional sets, right? So I think about the 3-dimensional set, and maybe, well, it will have some interesting facial structure, something like this, and maybe there will be some kind of curves and then convex hulls of different things. So I can look at this thing locally and consider a plane, design the facial structure of the set in a plane. And if I'm thinking about projectional exposure, so I want to understand whether I can or cannot project the whole cone onto a face. I can already see that things can go wrong in, say, this 2-dimensional picture. And then what I'm going to do, so once I have designed faces, say 2-dimensional faces, I can slap them on the 3-dimensional compact convex set, right, by adding some kind of a 3-dimensional coordinate to them, and then lift them to a cone. So I will design a 5-dimensional cone like this. And in this particular example, we managed to have this 3-dimensional face design that doesn't work, right? So we have 2 convex cones that, if I go down to 3 dimensions, right, they have this funny configuration. So this yellow thing in the 3-dimensional design will be somehow a face on which I either can or cannot project a certain structure. And these curves, together with this 2-dimensional thing, will give me as a convex hull, and then kind of attachment on the surface, and then lift that 5-dimensional cone. So I could design things in such a way that I can see from the 3-dimensional picture that it's impossible to project those curves onto, say, a disk like this. But I can project them on something larger. So if I add something on one side or on the other side, I can project them. And so those 3 things gave me 3 different cones. So I could say that, well, if I take 2 of them, they're a little bit larger, projection exposure works. If I take intersection, then it doesn't somehow. So I don't know how helpful it was or how useful it was. I just wanted to show how different things in convexity can be used for constructing things, right? Even something as complicated as 5-dimensional cones can be constructed using 3-dimensional intuition and 2-dimensional intuition. But still, I think we don't have very good methods for working with high-dimensional convex sets. So when it comes to this kind of problems, when we want to produce something that breaks some property or satisfies some constraints or some requirements, it's very difficult to construct those sets and check that things work or don't work, right? So that's basically the outcome of this. So thank you very much. I ran a little bit over time, but that was basically an hour. And tomorrow we'll talk about infinite dimensions. Yeah, and I'm happy to answer questions or take criticism or discuss things related to convexity and things like this.
Thank you. Thank you, Vera, for a very nice talk. So any questions from the audience? Any question? Can I have a quick question? So in your theory, I mean, you have a signatures, and then you try to find a collection of convex sets that satisfy that signature, right?
Mm-hmm.
But then how does it connect to the optimization problem? Because I thought that from the optimization problem, from the constraint, then you have the convex set. And so how does it connect? And how it's related? I'm a bit
so it's
confused.
so the way I see the relation, right, is
Yeah.
So there's two main things. So one thing is that when sometimes in optimization, we actually don't know why the method doesn't converge. Does it always converge what is the rate, right? So there's some uncertainty in some cases, and it actually happens that the problem is that we don't have a good example that will tell us that, okay, so for this example, the method doesn't converge. And so let's write this condition, and if it satisfies this condition, then we can prove that there's convergence. If it doesn't, then maybe look at this counterexample, it doesn't work, right? So that's one perspective, and it actually happens, right? So I will actually talk about some examples in infinite dimensional spaces tomorrow that shows some very interesting things about the convergence of projection methods. And another thing is exactly representation. So it's not about maybe a specific problem that I'm trying to solve, but it's about looking at the complexity, right? So it's like for the simplex method, right? Cleaning to cube, it shows that there is no hope that the known versions of simplex method are polynomial, right? Because we have those examples. It's exactly the same thing.
Okay, thank you. Thanks a lot. So any question, any other questions? Well, otherwise, then we thanks Vera again and see you tomorrow at the same time at 11 and the same link. Thank you.
Thank you.